Hello everyone, myself I'm Srivalya from Sri Venkateswara College of Engineering, Bengaluru, pursuing in third sem CSC Chanakya. Here we are doing the mini project. The topic is multiplexer design with the thread scheduling and the circular queue implementation. Introduction. The design of a multiplexer, particularly within the context of the advanced computational systems, necessitates a meticulous orchestration of thread scheduling and the data handling to optimize the performance and ensure the equitable resource allocation. Employing a circular queue paradigm is as a pivotal data structure introduces a methodological robust mechanism for the efficient and the cyclic data management. In the modern computing systems, efficient resource management and the task execution are essential for the optimizing the performance. This mini project focuses on the design of a multiplexer, utilizing the thread scheduling and the circular queue to manage the multiple tasks in a system. These concepts are fundamental in operating system and the network management and the real-time systems. Literature survey. Multiplexer design in the system architectures. Multiplexer design has been extensively studied for its role in the digital and the communication systems. Early research focused on the optimizing multiplexer configurations to reduce the hardware complexity and enhance the data routing efficiency. Thread scheduling in the multi-threaded systems. Thread scheduling algorithms are the cornerstones of the multitasking operating systems aimed at the maximizing the CPU utilization while ensuring the fairness and the reducing the latency. Enhance scalability and the adaptability. The modular nature of circular queue structures the flexibility of thread paradigms allow the multiplexer design to scale efficiently with increasing. Applications. Multiplexer design in thread scheduling. A multiplexer typically combines the multiple input signals into a single input. In the thread scheduling, these can be metaphorically applied to the scheduling process, where a multiplexer might select which thread should be executed at any given time based on the certain scheduling criteria, like priority, time slice, or the resource availability. Circular queue implementation is implementation the thread scheduling. Round robin scheduling. The circular queue can store the threads in a queue structure where the first thread gets the CPU time slice and then the thread move to the end of the queue once it is slice completed. Queue management. The circular nature of the queue ensures that no thread are missed and helps in maintaining a fair execution order. Benefits. Fairness. Every thread gets a chance to execute within a fixed time window. Efficiency. The circular nature allows efficient reuse of the queue without needing to move threads around a linear structure. Scalability. The system can easily scale to handle large number of threads without excessive overhead. Okay, here is the code which demonstrates the simulation of multiplexer design using thread scheduling and circular queue implementation. First, we are including all the standard libraries using hashtag include. Then we are implementing the buffer, which is the vector to store elements. Next, front and rear, which indicates the track for first and last elements in the queue. We are using the buffer vector t dot buffer, which stores the vector values. Next, we are using the size, which here we are using circular queue which has size front and rear. Front and rear, it tracks the first and last elements in the queue. Size is used to give the maximum capacity of the queue. Mutex and CV, they are the mutex and condition variable for thread synchronization. So we are using key method, which is empty is full, enqueue and dequeue. Is empty, it check if the queue is empty. Is full, it check if the queue is full. Then enqueue, it adds item to the rear of the queue, and dequeue, it removes the element from front of the queue. Next, we are using a multiplexer class. Here we are using a private keyword to define the int and queue and running of this thing. Then we are using a public keyword where we define the multiplexer. We are using for constructor, producer, consumer, and stop. Constructor, it accepts the circular queue reference to operate on. Producer, thread that init
data into circular queue. Consumer threads that dequeue data from circular queue, stimulating data processing. Stop gracefully terminates the producer and consumer threads by setting run flag to false. Next, we are using a main function, and we are using a for loop for giving the producer consumer threads. Then we are defining the main function queue initialization, where we are using the circular queue to create objects with capacity of 5. Then multiplexer object which passes the queue to a multiplexer instance. Next, thread creation, which starts with 3 producer threads and 2 consumer threads using std.thread. Producer and consumer operates concurrently, accessing shared queues. Execution period. The thread runs for 5 seconds, stimulating continuous production and consumption. Thread cleanup calls mux.stop, where it is a signal for thread to terminate, and joins all the thread to ensure orderly termination. Next, the key features are thread synchronization, which producers wait in a queue is full, consumers wait if the queue is empty, using std.condition variables. Next, concurrency. Multiple producer and consumer thread operate simultaneously. Scalability. The modular design allows easy adjustment of thread counts and queue size. Real world relevance. Demonstration how thread scheduling and circular. So these are all the codes, and the output comes as producer um, DQ or NQ. So it takes a period of 5 seconds for giving the output, and you get almost around 15 lines of output.
Here are few results and outcomes. Results are reduced computational overhead, enhanced scalability and adaptability, improved system latency. In reduced computational overhead, the use of circular queues minimizes memory fragmentation and the overhead associated with linear queue implementation, and enhanced scalability and adaptability. The modular nature of circular queue structure and the flexibility of thread scheduling paradigms allow the multiplexer design to scale efficiency with increasing workloads. This adaptability ensures the system can accommodate dynamic variations in task intensity without degradation performance, making it suitable for diverse applications including cloud computing, IoT, and also high-speed networks. Next is improved system latency. Thread scheduling methodologies, particularly those leveraging real-time and priority-based algorithms, synchronize thread execution, thereby minimizing contention and execution delays. Circular queue implementation further augments this by expediting data enqueue and dequeue operations. Together, these mechanisms contribute to a substantial reduction in system latency, ensuring fast response times in time-critical applications such as communication systems and embedded controllers. The real world application outcomes. In real world application outcomes, where we can see network on chip architects and embedded systems and also cloud computing. And in network on chip architects, we can see improved bandwidth management and reduced packet contention. Embedded systems, we can see enhanced performance in constrained environment and enabling real-time data. In also cloud computing, we can see efficient task scheduling across distributed nodes, leading to higher throughput and also resource utilization. Where in conclusion, where we can see the multiplexer integration with thread scheduling reduces latency and contention for resources. Circular queue implementation provides a memory efficient cyclic data handling mechanism, enhances resource allocation and optimizes task execution order in multi-threaded environments. Future direction focus on integrating adaptive intelligent scheduling algorithms for better efficiency. Here are few of the reference works which we have taken from digital integrated circuits and also scheduling algorithms for multiprogramming in hard real-time environment, Journal of the ACM, and also Addison, Welsi, and also from the optimization of circular queues in real-time systems, and also hardware-assisted thread scheduling using circular queue from IEEE transactions on parallel and distributed systems, and also circular queue-based schedulers in network on chip architectures, ACM transactions on embedded computing systems. Thank you.